Hi, ladies and gentlemen. Today is the next part of our fluids lesson, and today we are going to be talking about hydrodynamics, which is also the science of moving fluids. Now, whenever we talk about moving fluids, there are a couple terms I do want to bring up, which we're not going to use too much, but just so that we understand. And those terms are laminar versus turbulent. Laminar versus turbulent simply talks about the friction that exists within fluids itself. As fluids are flowing along, normally they're going to act against each other. And that's where we get the idea of turbulence. But for our purposes, we are going to be dealing with ideal fluids, laminar, or also called streamline, which simply deals with as little friction within the fluid as possible. And if we talk about moving fluids, keep in mind that we're going to be dealing with anything that might be shooting water out, and there's going to be a certain amount of water flowing through the pipe and coming out at a given rate, and we call that the flow rate. So flow rate is defined as the volume of fluid that's traveling per unit time. Okay, so if I actually had to make this a formula, so the flow rate, FR, would equal to volume over time, which is the same thing as meters cubed per second. Okay, so flow rate is literally how much fluid is coming out per given second. Now the thing is, volume, well, let me bring it up to this board over here. Volume within a pipe can also be stated as, if it was just a circular pipe, the area of the pipe times the length of the pipe, which is really the same thing as saying pi r squared times the length. So this is a formula for volume of a cylinder. So if we take this formula for volume of a cylinder, and we say the flow rate is equal to volume over time, or the area times the length divided by t. What's interesting is that with length divided by time, well, length, distance divided by time is the same thing as velocity. So area times velocity is also equal to flow rate. So we can use either one to solve for flow rate, the unit still being meters cubed per second. If we do one quick practice problem with that, okay, so over here, they say if the flow rate of a liquid is measured at 8,000 meters cubed, okay, sorry, there's a small typo, that should say 8 times 10 to the negative third meters cubed per second, going through a 2 centimeter radius pipe. What is the average fluid velocity in the pipe? So they're telling us that the flow rate is equal to 8 times 10 to the negative third. The radius of the pipe is 2 centimeters. And of course, we don't use centimeters, we use meters, so we're going to convert that to 0.02 meters. So when they're asking us for the velocity, flow rate, of course, is equal to area times velocity. So therefore, the velocity is simply equal to 8 times 10 to the negative third meters cubed per second, the flow rate, divided by the area. The area, of course, of a circular pipe would be pi r squared. So that would be pi times 0.02 meters squared. And if you work this out on the calculator, you get 6.37 meters per second. Okay, 6.37 meters per second. As a follow-up question, though, how much time would it take, let's say, to fill up a bucket? So let's say that pipe where is dribbling out the water. There's the pipe, there's the water coming in and spilling out into a bucket below. Okay? And this bucket, let's say, has a volume of 0.5 meter cubed. It's a huge tub of a bucket. And how much time would it take to fill up that bucket? So using the same flow rate as before, I'm able to calculate how much time it took to fill up the bucket. So if I know that the flow rate was 8 times 10 to the negative third, so flow rate is also equal to volume over time. So therefore, my time would equal to my volume divided by flow rate. Okay? Please note the difference, by the way, between a capital V and a lowercase v. Over here, we have a lowercase v. I draw that with a small little wingtips, but just to represent velocity. A capital V will be drawn much bigger and straighter. That means volume. So in this case, if I take the 0.5 meters cubed and divide it by the flow rate, I would see that it would take a time of 62.5 seconds. So that's how we use flow rate. Okay. So we could put that into the box as well, but what's more interesting is what the flow rate formula means with regards to what happens when pipes get narrower. Okay? I mean, if you think about it, a certain amount of fluid has to pass through the pipe in a certain amount of time. And if you have smaller area than before, how are you going to get as much fluid out? So of course, if you're going to get as much fluid out, it has to be moving faster. So the flow rate formula, okay, we know is equal to volume over time, or area times velocity. But the flow rate is a constant value, meaning it doesn't change. So technically, if I'm changing the area, I'll change the velocity to compensate as well, meaning the smaller and smaller the area gets, the faster it goes. If we take a look at this animation over here, okay, right now we have water flowing through a pipe. And if I change the diameter of the pipe, okay, hopefully you'll notice that the velocity slowed down significantly when I changed the diameter of the pipe. If I made it even skinnier, on the right side, the velocity increased. So basically, the point here is that the area of the pipe is inversely proportional to the velocity. Or in other words, A is inversely proportional to V. As one goes up, the other one goes down. And we see this in everyday life all the time. And if you think about it, let's move out this example over here. Okay, let me just clear that. If you take a quick look at this YouTube clip of a hose.
If you haven't already heard of the Bullseye Nozzle, allow me to explain it. The Bullseye Nozzle is a revolutionary, patented garden hose nozzle made in the USA. This small brass nozzle combines power and water conservation so effectively that US and Canadian firefighters use it extensively in their fight against forest and wildfires. How does it work? The Bullseye Nozzle generates power and conserves water via its unique patented closure system. This system uses a self-contained rubber gasket to constrict the incoming flow of water.
And when he says to constrict the incoming flow of water, that means, of course, to simply make the volume smaller. And make the area smaller. And when you make the area smaller, of course, the velocity is going to increase. And you can see how fast the water is coming out.
By constricting the flow of water, velocity is increased and a powerful stream of water is generated. This stream not only delivers maximum power, pressure, and reach, but it eliminates overspray.
Okay, so let's move past this. And let's actually do a quick practice problem. Water flows into a house at a velocity of 15 meters per second through a pipe that has a radius of 0.4 meters. The water then flows through a smaller pipe at a velocity of 45 meters per second. What is the radius of the smaller pipe? So when we deal with flow rate, you're simply dealing with A1V1 equals to A2V2. So the area is a circle, so we're going to make that pi R1 squared times V1 equals to pi R2 squared times V2. To me, it's just easier to put everything into the equation rather than solving for each individual area, though you could do that as well. And you can see that there's a pi on both sides, so let's just cross that out. So in the end, if I'm looking for the radius of the smaller pipe, I'll just plug in my numbers. R2 ultimately is equal to R1 squared times V1 divided by V2, square root, and you get as your answer, let's see, so that would be 0.4 squared times 15 divided by 45, square root that. So you get the new radius to equal to 0.23 meters. Okay, so you guys can see as one goes up, the other one goes down, and it's inversely proportional. If the area were to double, that means the velocity were to half. Okay, in this case, the velocity tripled. Okay, so if the velocity went up by 3, that means the area had to decrease by 3. But because it is the radius, which is the square sign, the square root of 1/3 will be 0.5, and you multiply that by the original radius, and that gives us the exact same answer. But I want you guys to understand the velocity and area are inversely proportional to each other. So if you take a look at a different question above, okay. Now in this case over here, the diameter diminished from 3.6 to 1.2 meters. Okay, I'm going to do this without even doing my calculations. I mean, I could use A1V1 equals A2V2, but I know that overall, if the diameter is 1/3, that means the radius is 1/3 as well. So radius is 1/3 the value of before. But because it is a pi r squared, that means my radius or my area is really 1/9 of the original value. So therefore, my area is going to be 1/9 the original value, which means if area goes down by 9, my velocity is going to increase by 9 times. So if the original velocity was 3 meters per second, that means my new velocity is equal to 27 meters per second. If that is confusing, you can always just plug your numbers actually into the problem itself, but I just want you guys to understand the basic idea of using multipliers to solve for this also. Okay. And the next part of the lesson is going to be talking about a man named Daniel Bernoulli. And Bernoulli was a famous mathematician who also basically came up with this formula for conservation of energy within fluids. Okay. So basically, Bernoulli's principle was about the idea of plus pressure within fluids. So if we were to actually write out his equation, it would just be setting the energy at one location equal to the energy at a secondary location. So if we look at our formula over here, and just move up a little bit, okay? So basically, at this first location, we take the pressure plus the energy is going to equal to the pressure plus the energy at the second location. So the types of energy we dealt with were potential and kinetic. Now, the thing is, for potential energy and kinetic energy, it's 1/2 mv squared and mgh. But the idea of mass is a little difficult to use because there's water constantly flowing through. So it's not just one steady mass that's flowing through. So rather than using mass, Daniel Bernoulli used the idea of density. Okay, so we're going to use density, rho, instead of m, for when we write out our equation. So basically, if we're talking about the energy at this location, so it's going to be pressure plus the potential energy, which is going to be rho g y, so that's potential energy, plus kinetic energy, which is 1/2 rho v squared, and that's going to be your kinetic energy. And this is a constant value. So we can set P1 plus rho gy1 plus 1/2 rho v1 squared equal to P2 plus rho gy2 plus 1/2 rho v2 squared. It's basically saying pressure plus energy equal to pressure plus energy at a different location. So if we actually, let's take a look. Take a quick look at this diagram then. Okay. So if I were to actually write this out, I would be able to write P1 plus rho gy1 plus 1/2 rho v1 squared is going to equal to P2 plus rho gy2 plus 1/2 rho v2 squared. Now, y1 and y2 are given over here, although just like with potential energy, you can make the bottom wherever you want. So technically, you can make that part the bottom. So how much y1 would there be in this case? Of course, if it's at the bottom, y1 would then equal to 0. What's interesting to note is that the velocity, okay, is going to be dictated by our flow rate formula. So if the pipe is changing diameters, it's going to change velocities. So in this case, okay, we see that the second location, the pipe is getting thicker. So we know that V1 is going to be greater than V2, and we could actually use A1 V1 to equal to A2 V2 to solve for the second velocity. Of course, if the pipe didn't change diameter, that means that the velocity did not change at all while it's going up. You might be thinking, how can it not be slowing down if it's going up? Well, for us, you have to remember, the pipe is full of water. I mean, there's water all inside the pipe. So one water pushes the next, pushes the next, pushes the next. The fact is, the water can't slow down because there's always something behind pushing it along. So rather, as it goes up, if the pipe radius did not change, the speed would not change, but the pressure would. Okay, and we'll start talking about pressure as well. And if we take a look at our drawing in our example from before, let's just remove all this over here. Okay, and reset it. So therefore now, if I'm going to be changing the height, notice the velocity never changed because the diameter of the pipe never changed. The only way the velocity would change would be if the pipe itself got skinnier or fatter. So if I make this pipe skinnier now, it would be speeding up, as you can see in the values for velocity. If I made it thicker, if I made the other one thicker than the before, you can see it's going to be slowing down. Okay. Rather, what changes as you're going up, as I said before, if your pipe does not even change speed as it goes up, what exactly is changing? And notice over here that the pressure decreased when it went up. So if you think about an apartment building, which floor has the best water pressure for like a shower or for a bath? The top floor always has the worst pressure, and the bottom floor usually has the best water pressure. But the flow of the water, the flow of the velocity is going to be exactly the same. Let's use, okay, so let's clear this. Okay. Now, with Bernoulli's equation, of course, since it is conservation of energy, there are a few things you have to understand that can be crossed out. So, if you have anything that's open to the air, if any end of either end of the pipe is open to the air, okay, open to the air automatically means that the pressure is going to equal to atmospheric pressure. Or in other words, 1 times 10 to the 5th newtons per meter squared. Okay? So if your pipe is open on both ends, and you write the formula, P1 plus rho Gy1 plus 1/2 rho V1 squared equals P2 plus rho Gy2 plus 1/2 rho V2 squared. Okay? So if both ends are open to the air, that means P1 and P2 both equal to 1 times 10 to the 5th. If they both equal to 1 times 10 to the 5th, then therefore you can automatically cross them out. And if you were to cross them out, notice every single portion of the equation now has a row. So if you cross out P1 and P2, then if you wanted to, you could cross out all the rows as well. And it becomes a pure potential energy plus kinetic energy equals potential energy plus kinetic energy equation. Okay? So that's if both ends are open to the air. But if either end is open to the air, then you automatically set one of them equal to 1 times 10 to the 5th. If the tube remains level, well, actually, let's do it if the fluid is initially not moving. So let's say you had a bucket of water, okay, and someone shoots a little hole into that bucket of water, actually. So the bucket of water starts leaking out. So in this case over here, we have two locations. We have the water at the top versus the water that's actually leaking out. But the water at the top isn't really moving down noticeably at all. So if the fluid is initially not moving, that means your initial V1 will equal to 0, and your 1/2 rho V1 squared is going to cross out. Okay? Though I do want to mention, though, at this point, of course, that if 2 were at the bottom, that means your rho Gy2 will cross out. So if we actually put this into an example, let me draw it out for you guys. Okay, if there were a hole in the bucket and there's water leaking out, we have location 1, we have location 2. If we were to write this out as our formula, P1 plus rho Gy1 plus 1/2 rho V1 squared equals P2 plus rho Gy2 plus 1/2 rho V2 squared. Okay, I know it looks really, really long and scary. But notice, both ends are open to the air. So P1, P2 crosses out. At the top, initially the water is not moving at all. So 1/2 rho V1 squared crosses out. Location 2, we'll consider it as the bottom of our problem. So there's no height at the bottom. So really you end up with rho Gy1 equals to 1/2 rho V2 squared. And of course, since there's density in both, that crosses out too. So in the end, notice if I was looking for speed, is equal to radical 2Gy, which is our original formula for speed. Of course, this is only true if both ends are open to the air, but notice how everything ends up canceling out, and that's going to happen in a lot of fluids problems. Okay, so going back to here, Now this last part, if the tube remains level, is actually the most interesting part of Bernoulli's formula. Okay, so if the tube remains level, even if it's changing diameters, okay, so if we take a look at, let's see, this example over here, okay, if the tube is remaining level, meaning that the midpoint of this picture is staying exactly the same, that means y1 is going to equal to y2. And if y1 equals to y2, that means rho g y1 and rho g y2 cross out, and you're left with P1 plus 1/2 rho V1 squared equals to P2 plus 1/2 rho V2 squared. You might be thinking, okay, so what's the big deal? Well, let's think about this. As it goes from location 1 to location 2 in this problem, we know that the speed is increasing. Okay? We know the speed is increasing because the area got smaller, so the velocity got bigger. Now, if the speed is increasing, what has to happen to the pressure so that it equals the same amount as before? In this case, the pressure is actually going to decrease. Okay? So for what I want you guys to understand is that as the velocity of a fluid increases, the pressure decreases, and vice versa. The velocity goes down, pressure goes up. And we actually see that in our picture over here, how we have less pressure in this location as compared to the original location. This is just of course, just a picture. But if we take a look at our animation from before again, as I said before, we have a thicker pipe going to a skinnier pipe. As the pipe gets skinnier, the velocity goes up. When the velocity goes up, the pressure went down. Okay? So all these factors play a role in energy for fluids. Okay. So what does this have to do with real life? Well, this explains how a lot of things work, including an atomizer. An atomizer is basically whenever you take a perfume bottle and you spray in the perfume bottle, it sprays out as a mist. Or whenever you guys take a bottle of Fantastic or cleaning your windows at home, whenever you squeeze that trigger, how exactly is the fluid coming up the tube and out? Or even if you just take a water gun, right? When you take a water gun and you're squeezing the trigger, why does the water just shoot out? Well, you see, the way it works is whenever you take a trigger or your air blowing across, when you blow the air across, you're increasing the velocity. When you increase the velocity, you decrease the pressure. And if you guys remember from earth science, fluids will always move from high pressure to low pressure. So basically, all the air pressure that's outside pushing on this fluid is going to force the fluid down and go up the tube, which then basically gets blown out as a fine mist. So that's how an atomizer works. If I were even to just take a sheet of paper, if I blow across the top of the paper, you might think, okay, I'm just going to be blowing the paper down. But watch. If I blow across the top of the paper, you can see the paper is actually moving up. Now, a lot of people thought this was very interesting because they then realized this could be used to help mankind fly. And this is how the airplane wing works as well. So basically here, when the fluid, in this case air, strikes the wing, it gets split up, okay? But the air here has to basically match the air coming out over there as it goes past the wing. So as it splits up, there's more distance to cover across the top as opposed to just straight down below. So because that there's more distance, it has to actually travel faster to catch up. If it's traveling faster, so you have a higher speed, that means you have a lower pressure. So with a low pressure on top, you have a high pressure below. Air will literally take that difference in pressure and push it up. According to the formula that we've learned before, delta P is equal to F over A. So with an airplane wing, when you have low pressure versus high pressure, we can take the difference in pressure and take the area of the wing itself that's attached to the plane, and that's how much lift force is generated. Which is why airplanes need a runway to take off. They can't take straight up. They have to start traveling along the runway first, because when it's traveling along the runway, it's creating a greater and greater difference in the air pressure as it's going. Okay? Eventually that difference is great enough for it to actually take off. Okay. So, sorry about the sound. Okay. So basically, this is just a representation of an airplane wing. Okay. Green is the lift force. Blue is just the weight of the wing itself. As you guys can see, when the wing is perfectly flat, there's no lift force being generated. But as soon as you increase the angle, okay, as soon as the air has to go faster over the top and slower below, you end up with low pressure here, high pressure down there. And again, so delta P equals to F over A, and you create a lift force. But what's interesting to note, if you've ever seen really, really, really fast cars, they always have giant spoilers. And the spoilers are angled in the opposite direction. And so if you have to imagine, here's a car. And here's a giant spoiler on the back of the car. You see, cars themselves, if I was driving the car in this direction, have a Bernoulli effect. If they drive too fast, they end up with low pressure above and high pressure below, and the car will actually come up off the ground a little bit. So whenever they're trying to generate a land speed record for cars, they can't go too fast because the car actually comes off the ground. To prevent that from happening, they put a spoiler in the back, which is basically an upside down airplane wing. So that will actually generate a lift force. When they have high pressure over here, low pressure over here, it will actually generate a lift force in the opposite direction. So Bernoulli basically explains why airplanes fly, why sailboats sail, and why curveballs even curve. It's all due to a difference in pressure, which causes there to be a creation of a force. So let's do one quick problem with Bernoulli. And we've kind of seen the same diagram from before that I was drawing for you guys. A stray bullet penetrates the town's water tank and causes a leak. If the top of the tank is open to the atmosphere, determine the speed at which the water leaves the hole when the water level is 0.5 meters above the hole. Sorry about the spelling. So we see our two locations. They say this is location 1, this is location 2. Notice both ends are open to the air. So when I do P1 plus rho GY1 plus 1/2 rho V1 squared equals P2 plus rho GY2 plus 1/2 rho V2 squared, I can automatically cross out my pressures because I know that they're both open to the air. If I assume that this is the ground level, I know that the height at the ground level would be equal to 0. And the water isn't really moving at the top very quickly. So it's almost negligible, in fact, with the speed it's going down. So the velocity at the top is going to equal 0 as well. So then we end up with 1/2 rho v1 squared equals to rho gy2. Rho's, of course, will cancel out. So velocity will equal to radical 2gy2, which in this case will equal to 3.16 meters per second. Okay. The next question actually turns this into a projectile motion question. If this entire thing were above the ground, right, then basically how far will it travel when it hits the ground? But I'm not going to do that with you. Projectile motion is something that you should be able to do yourself. But I just wanted to point out that it's easy to mix original mechanics equations and problems into fluids as well.